Okay, so we are going to discuss just one question, and which is that there is a certain circular object like a sphere or a disc or a cylinder, and it has been put on the ground with a certain spin. Hello, say omega, and with a certain velocity, say u, wherein u is not equal to omega r, right? So what is going to happen, guys, according to part 1? If it is not pure rolling, what is there? Whose job kicks in?
Friction.
What?
Friction.
Yeah. So friction is going to play a role over here, right? And we know, we have discussed, if u is greater than omega r, then friction has to be backwards. If omega r is greater than u, then friction has to be forward. And it is doubly helpful in bringing it for pure rolling by reducing u, increasing omega, or the other way, by reducing omega and increasing u, right? So that was the point of the class previously. Now in this class, to solve the question that after some time when friction has kicked in and it has helped us to achieve pure rolling after a while. So after a while, what is happening is the body is having a nice V and a nice omega. So omega dash and V dash, such that your V dash is equal to R times omega dash. Okay. So, so if that is the job of the friction, when it happens, then technically the friction disappears and the body keeps on pure rolling. Okay. So what would be the V dash and omega dash is the point today. Now you can solve it in two ways. One is by the concept of angular momentum, and other is the old concept of your accelerations and angular accelerations. So what is the concept of angular momentum? So angular momentum, just for recapping, what is angular momentum? If there is a body, whatever is the body, is rotating about its center of mass with omega, and the center of mass is traveling, it is traveling in this direction with v, no relation of omega with v, because it is just freely rotating and the velocity has been given. It's not like rolling on the ground or something. And you have a certain point from where you want to study the angular momentum. You study angular momentum from a point. Okay. Then, guys, any idea? This distance is r. So we call from O to the center of mass as r vector. So that's your r vector. Okay. From O to the center of mass, not the other way around. So what is angular momentum? Anybody tell me? So angular momentum, as all other formula in rolling in rotational motion, angular momentum will be, first, you don't even think that the body was a rod or something. You just think that the body was a point mass over here. And one is asking the angular momentum of that point mass going with v velocity from the point O, r distance away. So you just think of it as a point mass. Is that clear? Going with that. If you think of it as a point mass of m, then what is the angular momentum? Anybody?
MV
M
cross
R
R.
cross V. No, not V cross R. R cross V. Okay. V cross R will give you absolutely opposite of that. So what is the R vector and how do we do a cross product? To do a cross product of say this was A, this was B. First you have to lift the B and put the tails together. So you'll have to redraw like this is B, this is A. Then if it is a B cross A, then you turn your fingers from B towards A. So when you do that, if you can look at me, then the thumb is going inside the plane. So your B cross A, B cross A is going to come as inside the plane, wherein if you do a cross B, it comes out of the plane. So A cross B will have exactly same magnitude as B cross A, but it will come out of the plane. I'm just recapping. This is not the agenda for today. I hope you know this cross product and all. If not, you'll have to brush it up a bit, or you can ask me a doubt over here if you want to ask. So, for a point mass, angular momentum was this. Is that clear? Is that clear? Is that clear? It is even better to write like this. If I say R cross V, that means I've extended my R. I've put the foot of the R. My R goes this way, and this is the angle I'm talking about, right? So what is it? It is MRV sine theta, right? Cross product, right? Right? Is that clear?
Yes.
So this formula we can study in two ways. M R sine theta times V, or R times V sine theta. Okay, this is your perception. Okay, in many cases, looking at the picture like this, and I'm doing a MV into R sine theta. It is generally written as MV into R perpendicular. Or I am looking at MR into V perpendicular. Both gives you the same answer. Is that clear? Is that clear? The point is, cross product would have given you a very ideal answer if you were studying this is your R and your V vector was something like this. Then it is simply your mass is going this way. Then your L was simply MR into V. You don't even have to do a cross product. Cross product will result in MRV sine 90. Okay, sine 90 and sine 90 is 1. Is that clear? So the ideal scenario of a cross product is that the two vectors are 90 degrees to each other. Is that clear? Is that clear? So when we study it as MR sine theta V, which is many a case you will be doing, particularly in angular momentum, okay, which is I mean, more than 50% of the time you will love to do it as MVR perpendicular. So what the hell is R perpendicular in this diagram? In this diagram, if I take the vertically opposite angle of theta, I'm just doing a recap. Okay, I'm going to teach something else today. I'm just doing a recap of what is angular momentum in a rushed up way. So R sine theta is how much? This guy is your R sine theta, right? 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 So I call it as R perpendicular. From the line of motion of V, what was the offset or what was the perpendicular distance of the velocity vector from the point of consideration, R perpendicular. So if you have an eye on the R perpendicular, then you can simply write MV into R perpendicular. Is that clear, guys? The other way of studying the same thing is, okay, I don't want to disturb my R. I will see the components of the velocity. So the velocity will have two components. One along R, which doesn't provide any angular momentum because it doesn't create any angular change from the point of study. If somebody is going along the R, hardly any angular change or no angular change. And it has got a component which is perpendicular to R. What is this? This is V perpendicular. This is nothing but V sine theta away from the theta. So this is not going to create any angular momentum, but this guy, V perpendicular, is going to. So you take the whole of the R and the whole of the P perpendicular. This is this formula. Is that clear? Is that clear? So many a times when you're studying, say, angular momentum of a satellite going around a planet, you would rather like to go by this formula. You don't care about the R perpendicular. Okay. So it is a situational choice. What do you want to do? Is that clear? Is that clear? Or you simply do your normal math that I have taken the full R, I have taken the full V, this is your full V, and I'm simply using the sine of the angle between V and R. I don't even care what is R perpendicular, V perpendicular, and stuff like that. Any which way, this is your angular momentum of a point body. Is this clear? Is this page clear? Is this page clear? This is the definition of angular momentum. M R cross V. Okay, or M is just a constant, so you can write R cross MV. MV is linear momentum. Okay, R cross P you can write, or M R cross V. Is that clear, guys? So coming to this, a body which is having a, which is not a point body, how to write the angular momentum? First thing is you write as if it was a point body. So if it was a point body, it was M R cross V. Is that clear? Which is MV R perpendicular, by the way. Okay. Then it is with respect to the center of mass, this formula, as if it was not having any rotation. Meaning to say, the body was rotating and going forward with V. What's the angular momentum? Versus body was not rotating, there was no omega, and going forward with V. This part M R cross V will still be the same because this mass is going with V forward. Whether it is rotating or not, this part is not going to change. But we know that if it is rotating, then obviously there is more angular momentum to it. Okay, so what is that? So that is with respect to the center of mass. What is the angular momentum? Then you come with the plus, and that is ICM, necessarily ICM, not I about this end of the rod or that end of the rod, necessarily ICM, because this M was CM, center of mass. So ICM omega, okay, again a vector. Is that clear? Is that clear? Is that clear?
Yes, sir.
Okay, so tell me in this situation which I have drawn, R cross V is which way? Inside the board, outside the board? R cross V. Tell me.
Sir, outside.
Inside the board. Okay, what is omega? R cross V is inside the board. R was this vector, put the tails together, R was this vector, V is this vector. And when you curl your fingers, right hand, when you curl your fingers from R to V, the thumb is going to go inside the board. Go from R to V. Okay, that's your theta. R to V, not V to R. Okay, is that clear, guys? Is that clear? What about omega? So again, you curl your fingers along omega, and it is also inside the board, right? So fortunately, in this figure, all the vectors things goes for a toss. You can simply say that L is equal to M R V sine theta or R perpendicular V, whichever way you want to write it, plus ICM omega. They simply get added because both are same direction, inside the board, inside the board. Is that clear? Is that clear? Is that clear? Is that clear? Is that clear, guys?
Yes, sir.
Okay. Had the omega been opposite, what it would have been? M R cross V minus I omega. Okay. Where inside is positive and outside is negative. Or minus MRV plus I omega. Is that clear? Is that clear? So the point is, these two parts are vectors, and we should not be like in too much of hurry to simply add them. Maybe they are not in the same direction, so don't add them. maybe they are 90 degree to each other. Then we'll have to square and add them. Okay. The other point, but I'm going to do very basics in these evening classes. So I'm just going to talk about two situations. One is the way I have drawn on top. Situation number one, I will say. Situation number two, say the body which is going forward with V was rotating this way with omega. Okay. Then if I consider my inside the board as positive, then L will be mRV sine theta, where theta is this angle, minus ICM omega. Do you understand this, guys? You have to be at least careful of minus or plus. Is that clear? If not, I'll repeat it. Is that clear? Is it clear? Is it clear?
Yes.
Okay, doubt, ask me. Okay, then I'll go to the question now. So everybody knows, you understand what is angular momentum? So coming back to the question. That's your question. After sometimes it clear holes. Okay. Now one more thing I don't understand. Angular momentum doesn't change and remains the same. There is no change of angular momentum unless until there is a torque, right? Right? Do you know this?
Yes, sir.
Do you know this? Yeah, that is how the torque was defined. If there is no change in momentum, if there is no change in MV, if there is no change, there is no force. Force is there if there is change, right? If there is change in MV, right? And how much is the force? Rate of change of MV, right? So much divided by delta T. Similarly, torque is rate of change of angular momentum. For conservation of angular momentum, it is simply if you can identify that there is no torque, then there is no change in angular momentum. Okay. So I would really like to emphasize on one point, which I really liked a lot. Okay. That we have few concepts. We have conservation of energy. Total energy initially is equal to total energy finally. Use that. Change of total energy is 0. And do some questions. That means you equate the initial energy, kinetic plus potential is equal to kinetic plus potential. Then we have momentum conservation, m1 v1 plus m2 v2 is equal to m1 u1 plus m2 v2. Momentum is conserved if there is no force. If force external is not there, and linear angular momentum conservation if torque external is not there. What is the highest likelihood of what happening? So as the chapters were taught, that is what it is. The likelihood of this happening is very low. Energy does get dissipated maybe because of friction and all and this and that. But if it is not, we can apply energy conservation. So that's your thought process when you look at a mechanics question. Can I conserve energy? Oh, no, I cannot. There was a collision here. That means I cannot. Unless until mentioned it is elastic collision. As soon as you see collision, you see friction, you say, okay, I cannot conserve energy. Okay. With friction, you can, in a way, that change of energy must be the work done by friction and all. But it is lower likelihood. With momentum, it is slightly higher likelihood. Even if there is a collision, even if there is a loss of energy, your momentum is conserved. So higher likelihood. Okay. The only thing is external force should not be there. Then even higher likelihood that even with external force, I just have to see torque is not there. Is that clear? And I can conserve. So this, if somebody becomes an expert on using angular momentum, which is, I know it is a pain in your brain right now, that how to use it, because it's a new concept, but if you can use it, it can be used in more cases than the others. Is that clear, guys? I'll try to again give you a mental picture of what I'm saying. If there is a, say, a body like this and I've got a force like this, can I conserve momentum? Will the momentum be conserved? No. Whatever was the velocity is going to increase, right? Why? Because there's the external force, right? 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 Yes or no, guys? Yes or no, guys? There's a force on a body. Will momentum be conserved? Yes or no?
No, sir.
But can you conserve angular momentum?
There's a
Anybody?
torque.
Can you conserve
Sir,
angular momentum? So you can conserve angular momentum because conserving angular momentum is around your point of choice. So let me ask you a few questions. Can I conserve angular momentum across this point A? Can I conserve angular momentum across this point B? Can I conserve angular momentum across this point C? Can I conserve angular momentum across this point D? Yeah, tell me. Be free, you can answer wrong.
sir, you can conserve across C and on at C and D, but you can't on A and B because there's a torque.
Okay, so you'll just see there is a force, and you will see that okay, some guy is talking about conserving angular momentum through these points. Okay, this force creates a torque about which point? There is a perpendicular, R perpendicular, so it will create a torque, F into R perpendicular. This is the line of force. There is a R perpendicular, so it will create a torque here also. So cannot conserve across this point. Will there be any torque about these 2 points? No, because there is no force on. There is no R perpendicular. Is that clear? The force is going through the point, so there is no torque, right? So you get such a big advantage that you can conserve angular momentum through any of these points wherever you want. Is that clear? Is that clear? So even with the force present, you can conserve angular momentum. Are you getting the point what I'm saying, guys? If you are getting it, just answer this one for me. This is the body, and I had a force F1, and I had a force F2. Momentum for sure is not conserved, energy for sure is not conserved, unless until I use the work done concept also. Angular momentum, maybe, I don't know. Is it conserved through any point you can think of? There should be no torque, and these two are two external forces. Is there any point it can be conserved? Is there any point it can be conserved? Fast, 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 fast. Yes, the person who answered this one.
Sir, I don't think so.
Yes, it can be conserved. So I extend F2 and I extend F1. So if I want to conserve angular momentum, if I put what is the torque of F1 across this point? 0. What is the torque of F2 across this point? 0. You get the point? That means I have a point through which the angular momentum is 0. So I can conserve the angular momentum still. Is that clear? So even with multiple forces, you may get a chance to conserve angular momentum. With a single force, you have a lot of chances. A lot of places are there where through which you can conserve angular momentum. Is this clear? Because it's a key point which will be used in the question what we have to solve. Is it clear? Is it clear?
Yes, sir.
Yes.
Now let us do the question then. Okay. Now this question will be done in two different ways. One, I would say, the longer way, and one is through angular momentum conservation. Now, since I was talking so much about angular momentum, so shall we do the angular momentum way, which is the shorter way? Generally, when I do after longer way, people say, "Oh wow." So, what do you propose? Okay, we'll do the long way. So that we come back to angular momentum and you get some. So let's propose a question. Say U was or 2U is equal to omega r. Omega is too big. Is that clear? Okay. And we have to find what do we have to find? The final pure rolling velocity. Is the question clear, guys? Is the question clear? Is it clear?
Yes.
Now, very surprisingly, how much is the mu, how much it is not going to matter in what you get your pure rolling velocities. Okay. If mu is very high, then this pure rolling will be achieved very quickly within few, say, inches, within few centimeters. If the mu is very low, then it will keep on over here like slipping. It will keep on slipping, keep on slipping, and the low mu will ultimately do its job of making it pure roll after, say, meters of meters. Okay, after many meters. But when it's achieved pure rolling, surprisingly the velocity will be same. So whether they give a mu value or not, it will not be used. Is that clear, guys? Is that clear? That's a unique thing. Okay. Is that clear? So let's assume the mu was mu, and ultimately it will not matter in the final answer. So first job is to do it from the longer way, do it from normal kinematics. So there is going to be friction, which is going to provide some acceleration or deceleration, and we will get the V dash using that. So can you tell me which way will be the friction? If omega r is equal to 2u, which way will be the friction? Part 1 concept, rolling motion part 1. Which way is friction? Backwards or forwards? Fast, fast, fast. Fast, fast, fast.
Sir, forwards.
Yeah, why any doubt? Man? Do the like this is the only thing we studied last 1 hour, last class, I mean the first class. The friction, the job of friction is to achieve pure rolling, right? So which is less? U is less than omega r, right? So if friction is forward, it will be able to increase the U. And if friction is forward, it is going to give an anti-clockwise torque, and it is going to reduce the W also, right? Omega also, right? Right? That is what we did, right? Is that clear? What are the other forces? The other forces are there, but not mattering at all. I'm not going to even draw it, I'll just draw it and rub it. One is mg, which is vertical, and the other is normal reaction. So your normal reaction must be equal to mg because the body is neither going up or down, and they cancel each other out. So the only effective force is F, right? Friction, right? So now we have to get the V dash velocity. So we know that V dash is U plus AT, right? Any doubt in this? Any doubt in this? So what the hell would A be? What is the acceleration? We have only one force, F forward. So what is the acceleration of the mass? What is the acceleration? F is equal to ma, right? Right? So the acceleration is how much? F by m. So V dash is equal to U plus F by M into T. Very low participation, guys. Very, very low. That's very disappointing. Is this clear? Is this clear, people?
Yes, sir.
Okay, what you don't know in all of this? You don't know F, you don't know T, you don't know V dash. We just got one equation. Is that clear? So the other equation will be for this omega becoming omega dash. It is a similar kind of equation. Can anybody speak out? What will it be? Like remember your circular motion. There's a body going with omega and you apply alpha on it for t time. Then what is the final angular velocity?
Uh, Omega final is
Omega
equal.
final is equal to omega initial plus alpha t, right? Right, guys?
Yes, sir.
Okay. From this lesson, you have learned that how to get your alpha, like how you got your A, F is equal to MA. How do you get your alpha? Torque is equal to I alpha, right? Right, guys? So having these things in your mind, can you tell me the equation of the omega dash? And initially it was omega. Initially it was omega, finally it becomes omega dash because there is an alpha acting. So which way is the alpha acting? Clockwise or anti-clockwise? Which way is the alpha acting? Which way is the torque? Direction of torque is direction of alpha. Which way is the torque? Who is creating the torque?
Anti-clockwise. Anti-clockwise, sir. Friction.
This friction is creating the torque, right? Right here, there's the body, there's the F. Obviously, it is creating a torque this way, right? The torque is alpha direction. So, torque that way is creating alpha, right? So, if I have to write in terms of alpha, how do I write it further? Omega dash is equal to omega. Tell me further what to write in terms of alpha. It is very similar to this one. What to write?
Omega plus FR by
Okay, we'll do the F and all later. Alpha के term में बोल दो. Tell me in the terms of alpha.
torque by this
No,
moment of inertia.
no. This equation, tell me in terms of alpha. Later on, we'll write alpha as torque.
Omega plus alpha into time.
Yeah, it is not plus. It is minus alpha t, right? This time.
Yes, sir.
Why? Because omega is one way and alpha is the other way. This is what is going to reduce your omega dash, which was too high. Okay? Sorry, which is going to reduce your omega, which was too high, and bring it to omega dash, which is a lower value. Is that clear? Then as we replaced A with F by M using this equation, obviously we'll replace alpha with what? Torque by I, right? Right, guys?
Yes, sir.
So how much is torque? Anybody? Speak your name and then speak the answer. What is the torque?
Sir, Anbu.
Janbu.
FR.
Yeah. Torque is the force, and I'm going to study the torque from here. Then what is the offset of the force? R perpendicular is luckily the radius of the body itself, right? So it is FR, F into R. That's the torque. So FR is the torque is equal to I alpha. So what is alpha? What is alpha? FR by I into T. That gives you second equation. Now tell me how many variables are there and is it good enough to solve? While I clear the board a bit. Do we have enough equations to solve or we need to know more? What is unknown? In the first equation, what is unknown? V dash is unknown, F is
Okay.
unknown, T is unknown. What's the unknown in the other one? Omega dash, F and T, right? So V dash is unknown, omega dash is unknown, F is unknown, T is unknown. Looks like too many unknowns, only two equations, four unknowns. But not really. Why? Because V dash and omega dash are connected. They are connected which way? This way, right? V dash and omega dash are related. They are pure rolling velocities. Ultimately, the pure rolling velocity which it achieves. So V dash can easily be replaced as R times omega dash. Any doubt about it? And very fortunately, F and T both are appearing together. So see how I write it. The first equation I write it as V dash, I write it as omega dash R is equal to U plus Ft as a single variable by M. And the second equation I'll write it as this one. This is the second equation. Okay. I'll write it as omega dash is equal to omega minus Ft as a single variable R divided by I. Is that clear? So Ft is like a single variable, and that is absolutely correct. Very high friction in very low time it will be able to achieve. F into T will be a certain number. When friction is very low, it will take very high time to achieve the pure rolling. But Ft is just it is F into T is, it is going to come as a certain answer. Okay. F and T are coming together in the equation. So now we can eliminate Ft, right? Right, guys? We can pick up Ft from one and put it into the other one. Is that clear? Is that clear?
Yes, sir.
Yeah. So just because it is written like this, what I'll do is I'll just write it over here in a very clean way so that we can add it up. So I'm just multiplying the M on top and bottom. Now it is only solving. So concept is done. It is over. If you have any doubt, you ask me right now. It is just solving and we'll get a certain answer. So that is immaterial, but I'll just do the answer while you are soaking in what has happened. You don't even have to look at what I'm doing further. I'm just eliminating Ft and getting my omega dash. So you don't even have to look what I'm doing. Okay, I'm just doing it. I'm just buying some time so that you look what happened on top and ask me doubts that what is this, what is that, ask me that. Got the point, guys? Is it clear? Is it clear?
Yes, sir.
So the final answer would be something like this. M R square. I'll just multiply R all over in the bottom also in the top also and add it up. Okay. I've just multiplied mentally R all over. Okay. And here also R. This and this is gone. Okay. And I just add it up. So MR square plus I, which is ICN omega dash is equal to M U R plus I omega. So much by so much is your answer. Is that clear, guys? Is that clear? Is that clear?
Yes, sir.
Now ask a doubt before I do it in the other way, which I will say that if you are okay in physics, you rather do the other way. That is faster. This is like more closer to all the concept. This method you can do other things also if asked. That if friction is actually given to you, then how much is the time? If friction is actually mu is actually given to you, then F is equal to mu into normal reaction, which is in this case mu mg. That means you know the F value. So you will know how much is the time and you'll know how much is the distance where it started pure rolling, those things. So it is, this answer is closer to the detailing part, okay? But it is longer to do. Shall I repeat what has been done or is it clear, everybody? U was there, omega was there, they were mismatching. First of all, the mismatch is U is more or omega is more. According to that, you'll choose the direction of friction. In this, U was less, so friction has to be forward to increase it. If U was more and omega was less, friction would have been backwards to decrease it. So once you get your friction, the first job is, friction is creating how much of acceleration you get it. That you get from this equation. Friction is creating how much of omega, alpha you get it. So you will try to get your alpha, that you get from this equation. The old equation is what you have been doing a lot. This is a bit newer equation, but it is as simple as F is equal to ma, torque is equal to I alpha. Torque on its own part is equal to force into force arm. So force is friction and force arm is the radius. So you'll get your alpha, you get your A. Once you get your alpha, you get your A. So the velocity, initial velocity due to the acceleration changes and becomes a V dash. Due to the acceleration, it becomes a U plus AT because there is acceleration. There is a force which is increasing it. And similarly, the initial omega, due to the deceleration, angular deceleration, it becomes less and becomes omega dash. And the formulas are, what is your circular motion formula? Similar to your linear motion formula. Omega minus alpha t, and then after that it is nothing, you have to solve it. You have to just eliminate your ft value and you get your omega, which I've done below, which is not a big concern. The big concern is, will you be able to write these line and this line on? Is that clear? Is that clear? Okay, so shall we do it the other way? Now we'll see whether we can conserve. Okay, first we'll do our homework and we figured out that the friction is acting and it is acting forward. No doubt about it. Then we will say, can I apply angular momentum conservation? I can start the whole story by saying, can I apply energy conservation? Oh no, lot of friction is there. There is rubbing and final energy is not equal to initial energy. Okay, initial energy is half m u square plus half I omega square, which is not equal to half m b dash square plus half I omega dash square. Why not? Because there was friction. If it was equal in one single go, one equation, we get the answer. We just replace your b dash with omega dash r and we get the answer. But unfortunately, this is wrong because energy cannot be conserved. So next will come that, what did I run there? Next will come that, can I apply linear momentum conservation? Again, the answer is no. Okay. And it is quite rubbish also. Linear momentum, initial linear momentum is, you don't care about the rolling, m into u. Final linear momentum is m into v dash. Is mu equal to mv dash? Obviously not. Why? Because there was force. There was force. Third question is, can we apply angular momentum conservation, which I was trying to teach you? What's the answer? Since so much of emphasis on it, obviously the answer is yes, we can apply. Right, guys? Because what I said, even with a force, where was that, man? Where was that? Even with a force present, we are drawn somewhere, right? Even with the force present, you can apply. So which is the point you will apply your angular momentum conservation? Anybody?
Sir, point of contact with the ground.
Most point.
Huh?
Where the bottommost point where friction is acting.
Okay.
Where it
I
touches
will
the
apply
ground.
from here. Okay. There's a reason why I'm applying from here. Because many people think, a misconcept that you are applying from here and later on you are applying from here. Which is wrong, which is not called conservation of linear momentum. It is not called L1 is equal to L2. When you calculate your L1 from this point earlier, and then you calculate your L2 from that point, then what the hell is the conservation? You have to calculate your L1 from a certain point and L2 also from the same point. So when the body has reached here and you are calculating your L2 from here, which is outside the body, then why not calculate your L1 also outside the body? So you have good practice of calculating your L's outside the body. Are you get the point? That's a key concept, okay? Very wrongly written in many books also because it hardly gives any change in the answer. But are you getting the point? Conservation of angular momentum means whatever was the point of consideration when calculating the first one, it should be the same point when calculating the other one. You cannot change your goalpost. Eh? Are you getting the point? Is that clear? Is that clear? So did I not demonstrate that if there is a body, if there is a body and there is a force, some person said that you can conserve from here also, here also, here also, here also, right? So the force is friction only. So why you guys are only hell bent on this point? It could be this point, it could be this point, it could be this point, okay? Is that clear? So let me conserve from this point. Is that okay? Is that okay, guys? Is that okay? Is that okay?
Yes, sir.
Yes, sir.
Is there any torque if I consider from this point? No torque. F is passing through it. F is passing through it. At the max, if I'm like very vigilant, then yes, mg will have a torque. Oh no, that's a spoiler. But then I have a normal reaction which also will have a torque, and thankfully n was equal to mg, so those torque will get cancelled, and hence only F is which is the one which could have provided a torque, which is not. Is that clear? Is that clear? Now comes the formula of the angular momentum. Okay, so angular momentum initially. Apply the formula correctly and tell me what will you get. I'll write some values. Say from here to there, this length is given as R1. Okay, to the center of the mass. This length is given as R1. Is that clear? What is the initial angular momentum? Anybody? What is the initial angular momentum? Anybody? Remember the formula was this, right?
MUR plus I omega.
Yeah. M-U-R. Why R?
Perpendicular distance, sir, from the force.
Absolutely right. Okay. It is M-U or M-R cross U, which we already discussed is what? Is the first part. The second part still remains, which we already discussed is what? M-R perpendicular times U, right? And what is R perpendicular? Perpendicular distance between the point of consideration and the line of U. Okay, so if I complete the line of U, then what is the perpendicular distance? This is R perpendicular. Fortunately, that is the radius of the circular body or not? Yes or wrong? Are you understanding what I'm saying? This is important. M R1 U sine theta, but R1, which is a big R1, and sine theta would be simply the radius of the body. Are you getting this point, guys? Getting the point, guys?
Yes, sir.
Yes, sir.
No, I rubbed a lot, man. Check. This was R1 immaterial. R perpendicular is, fortunately, R perpendicular is the radius. So my first part of initial angular momentum is M R perpendicular U, and R perpendicular is the radius, so MRU, as simple as that. Okay. Which way, clockwise or anti-clockwise? Clockwise or anti-clockwise? Say fast, I have to end the class now. Clockwise or anti-clockwise? R vector was this way. Clockwise or anti-clockwise? So R
Clockwise.
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 Clockwise means going inside the board, right? So this is inside the board. Then comes the other part, which is I omega, right? ICM omega. ICM. So we are just writing I for ICM for now. I omega. Omega is omega, which is given over there. Omega. This is clockwise or anti-clockwise. This is also clockwise. So we will just add them up. As simple as that. End of story. End of story. So what is the final angular momentum? What is the final angular momentum? So now again we have to see from this point. So who can tell? This long R2 is that. But is not R perpendicular still the R? R perpendicular is still the R, right guys? Right guys?
Yes,
Yes,
sir.
sir.
Therefore I did the first part. Okay, now you understand why I was doing the first part? R perpendicular is still the R. So what is the angular momentum now? So you forget about the history. Don't even see the initial position and all. What is the mass? Mass is of M. What is the R perpendicular? Radius of the body. What is the velocity? V dash. Okay. End of story. Which way? Clockwise, anti-clockwise? So again clockwise, so inside the board. What is the I omega? So what is I? I never changes, again never changes. So I is I. Which is the omega now? Now omega is omega dash. Is it clockwise? We have made clockwise in the question, so we'll write a plus. It is up to us. If you have made anti-clockwise, we'll write a minus, and automatically the question will get corrected. So this and this should be same. Question ends. As simple as that. The only thing is V dash, we can write it as R omega dash. Why? Because it is now pure rolling. So I'll just correct it and write it as M R square omega dash plus I omega. So if we equate the two, this and this equated, what are we going to get? Shall I just write? I'll write it. M R square omega dash plus I omega dash. So much omega dash is equal to what? The initial one, M R U plus I omega. Is that clear, guys? Is that clear?
So how did you get R square?
V dash is how much if it is pure rolling?
Omega.
Okay,
Okay,
what?
sir.
Huh?
Omega R.
Yeah, omega R. So we wrote it as omega R. No? So 1 R was already there.
Yes. Yes.
Okay. So now if you compare this answer with what we did here, right? No, where we did we do? Oh my God, I rubbed it or what? Look at the left hand bottom. Can you see that? And that answer, is it the same? Ditto same, right? Ditto same, right? Ditto same, right, guys? Is
Yes,
that
sir.
clear? Is that clear? I hope you are seeing the screen, this one, right? So the point is, what is the point? The point is, we get it very fast if you are confident of using your angular momentum. We got with almost nothing, doing nothing, just writing angular momentum initially and finally. Wherein with the other method, we have to write a lot. and we have to get it. But yes, obviously it is more closer to the mechanics which is happening. It is more closer to what is the actual thing which is happening. Okay. Okay, that's it. End of class. Shall I ask you a really tough logical question on this situation? Then you ask your all your doubts. Okay. The kinetic energy finally is half I omega dash square plus half mv dash square, and initially is half mu square plus half I omega square. The difference in the kinetic energy must be the work done by the friction. Initial kinetic energy is more, final kinetic energy is less. If I subtract it, it is equal to the work done by the friction. Okay. So is it equal to kinetic energy initially minus kinetic energy finally must be this loss of energy is due to the work done by friction, F into D, where D is so much. Am I right? Am I wrong? I'll give you 30 seconds to think. It's a very difficult question. I'm just kidding. It's not a difficult question. No, it is actually. No, it is not. All 30 seconds I'll be disturbing you. Yeah, what do you think?
I think so. I think you're correct.
Okay, it is wrong. Okay, why it is wrong? Why it is wrong? Because suppose I say it was pure rolling. Okay, suppose I say it was pure rolling or almost pure rolling. Then, I mean, okay, it's not a very good scenario to give you because friction will be zero. Almost pure rolling, some friction will be there. But the point is, okay, I'll give you a scenario which is a good scenario. Say there is an inclined plane and a body is rolling down, pure rolling down. Okay. Since it is pure rolling down, there must be something which gives the torque to pure roll, and there is a friction over there. I'm not explaining that, I'm just telling you. There is friction, then only it will pure roll down. Otherwise, it would have slid down. Instead of sliding down, if there is enough friction, it will pure roll down. Okay. And it rolls down d amount. How much is the work done by friction? Work done by friction is not FD. Work done by friction is zero. Work done by friction is zero because the body, when it is pure rolling, it is not rubbing across the ground. If the body rubs, if two surfaces rub, that is when it is skidding and sliding, then it only it is having a work done by friction. So here you will say it is skidding and sliding. Therefore, the confusion that will it be FD? No, it will be F into. It will be F into. It will be F into X, where X is the rubbing amount. Okay, so that becomes a little more technical question. So you guys can think about it later. And how much is the rubbed amount? Okay, and if you can write that, then you can write the conservation of energy also. So this is the toughest to write. I'm just showing you. You can do it by this. And the easiest to write was your conservation of. This is slightly easier. F is equal to ma torque is equal to I epsilon. This was the easiest. Any doubt in this? Ask me. Otherwise, sayonara. Either this page. Any doubt in this page or this page? Not the rubbed amount and all. I just said it for the ones who want to think and do it for themselves. Okay, nothing about the kinetic energy I'm going to tell you right now. Only on this page or this page. Any doubt? You ask me. Rest may go away. Thank you. Bye bye.
Thank you, sir.
Thank you, madam.
Thank you.